Today, I want to talk about prompting, and prompting is kind of a new paradigm as of a few years ago with interacting with models. It's now kind of the standard in doing so. And basically what we do is we encourage a pre-trained model to make predictions by providing a textual prompt specifying the task to be done. This is how you always interact with ChatGPT or anything else like this. So prompting fundamentals, the way that basic prompting works is you append a textual string to the beginning of the output and you complete it. And exactly how you can complete it can be based on any of the generation methods that we talked about in the previous class. Beam search, it can be sampling, it can be MBR or self-consistency or whatever else. So I put in when a dog sees a squirrel, it will usually into GPT-2 small, which is a very small language model, says be afraid of anything unusual. As an exception, that's when a squirrel is usually afraid to bite. So as you can see, if the model's not super great, you get a kind of not very great response also. But then I fed it into GPT-2 XL, and what it says, when a dog sees a squirrel, it will usually lick the squirrel. It will also touch its nose to the squirrel on the tail and nose if it can, which might be true. One thing I should note is when I generated these, I used like actual regular ancestral sampling. So I set the temperature to 1. I didn't do top P, didn't do top K or anything like this. So this is a raw view of what the language model thinks is like actually a reasonable answer. If I modified the code to do something else, actually, maybe I can do that right now. But if I modified the code to use a different output, we can actually see the different result that we get. Since I have it here anyway. Actually, sorry, I'll need to modify the code on my screen here. So I will set top K to 50 and top P to 0.95. So you see, I changed the generation parameters here. And I'll run all of them. You can see the result that we get in a little bit. But basically, so this is the standard method for prompting. I intentionally use GPT-2 small and GPT-2 XL here because these are raw base language models. They were just pre-trained as language models. And so when we prompt them, we're getting a language model that was just trained on lots of texts view of what is likely next text. There are other ways to train language models like instruction tuning and RLHF, which I'm going to be talking in future classes. And if that's the case, you might get a different response here. So when a dog sees a squirrel, it will usually get angry, scratch the squirrel, and run off. Some dogs may also attempt to capture the squirrel or attempt to eat it. Dogs will often attempt to pick up the squirrel and eat it first. It was more violent than I expected. Anyway. But anyway, I think that actually you can see that when I used the different generation parameters, it actually gave me something that was maybe more typical than lick. So lick is maybe a kind of unusual answer here, but anyway. Cool. So that's the basic idea of prompting. We tend to use prompting to try to solve problems also. So it's not just to complete text, although completing text is useful and important. Like I complete text in my Gmail all the time. It's constantly giving me suggestions about what I should write next, and I do tab autocomplete. On your phone, you're doing that. That's also using a language model. But very often we'll use prompting to do things other than just completing text. And when we do this, this is kind of the standard workflow for how we solve NLP tasks with prompting. The way we do this is we fill in a prompt template, predict the answer, and post-process the answer in some way. So prompt templates are templates where you will actually, that you will fill in with an actual input. And so if we have an input X, which is something like, I love this movie, our template will be something like X. Overall, it was Z, or overall, it was. And so if we do that, when we actually want to make a prediction, we will convert this into the actual prompt we feed into the language model by filling in the template. I love this movie. Overall, it was blank, and then fill this continuation in. A particular variety that we use very broadly nowadays, because a lot of models are trained as chatbots. But actually, even if they're not trained as chatbots, this still works to some extent, is a chat prompt. And so usually the way we do this is we specify inputs in a format called the OpenAI messages format. And this is what it looks like. We have a list of outputs. Each list is given a role and content. And here, so we have the role of system, and the content is please classify movie reviews as positive or negative. Then we have the role user, this movie is a banger. And then we have roles, system, message. So as the roles, we have the system, and the system is a message provided to the system to influence its behavior. It's to explain to it, like, how it should be working. And so you can see that this is explaining to the system how it should be working. User is the message input by the user. And so this could be just a single message, or if you have a multi-turn dialogue, it can be like user and then assistant, and then user and then assistant, and then user and then assistant. And that makes it clear that it's a multi-turn dialogue. So if you have a multi-turn dialogue in ChatGPT, that's how they're feeding it in into the system. So what's happening behind the scenes with these chat prompts? Basically, they're being converted into token strings and then fed into the model. So despite the fact that this is fed in this format, and it makes you think that maybe something special is going on, actually, in most cases, these are just being fed into the model as a prompt. So these are just kind of a special version of a template. So here we have, this is what the llama template looks like. So basically you have square bracket inst, and then for the system message, it's like angle bracket sys, close angle bracket, and then the actual system message. And then you have this closing out the system message, this closing out the instruction. Then the user is surrounded by inst, and then the assistant is just like a regular string. So this is what the actual textual string that's fed into llama chat models is. We can contrast that to some other models. So alpaca looks like this. So we have like hash, 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 instruction, colon, and then the instruction. For the user, there's no distinction between system and user. So it's like hash, 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 instruction, and then the user message, and then hash, 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 response, and then the assistant. So it's not super important which one we use here. The important thing is that this matches with what the model is trained. And I'll show you some example. I'll talk about that in more detail later. And we have a reference that I got this from. And there's this toolkit that I rather like recently. It's called Light LLM. It makes it very easy to query different LLMs in kind of a unified thing. So basically, you can query many different types of LLMs like OpenAI or open source models or other things like that. And what happens behind the scene is it basically takes the OpenAI messages format and converts it into the appropriate prompt format for whatever model you're using, or the appropriate API calls for whatever thing you're using. But this here, basically, if you click through this link, shows you, okay, this is what it looks like for alpaca. So you have the instruction response. This is what it looks like for Llama 2 chat. This is what it looks like for the Ollama. This is what it looks like for Mistral and other things like that. So you see all of these are very similar, but they're like slightly different, and getting these right is actually kind of important for the model doing a good job. Any questions about this? Yeah.
Like say you started off with this like input, and then you started going with similar input without using model and generating stuff.
Could you give an example?
Yeah, so say my account was a great movie, or this movie is great, but in front of it I put carrot this carrot, or yeah, for the is that break the model?
So it depends a lot on the model. The reason why this system message was input here in the first place was this wasn't originally a feature of OpenAI models. OpenAI was the first place to introduce this, which is why I'm calling it OpenAI messages format. They didn't originally have something like this, but they were having lots of trouble with people trying to reveal the prompts that were given to systems, like called like prompt injection attacks or like jailbreaking attacks or stuff like that. And so the models would basically reveal this prompt that was being used behind the scenes by whatever customer of OpenAI was like deploying a system. And so in order to fix this, basically what OpenAI did, I believe, like they don't actually tell you exactly what they did ever, but I'm assuming what they did is they trained their models so that the models would not output anything that's included in the system message. So the system message is used to influence behavior, but like they're explicitly trained to not output things that are included in there. And so if you put the actual thing that you wanted to evaluate within the system message, it might still predict the sentiment correctly, but it won't repeat the stuff that was included in the system message. Yeah. Yeah.
After we give it the input.
Yeah. So that's a great question. So typically this is hand created. So you create something like this. I have a bracket X here, but another way that people typically specify this is you just have a big Python string, which is like please specify and then you have and then you substitute in like the input into this place here. So you usually handwrite it. I'm going to talk excuse me in the end about some methods to learn these also, but I'd say like 95% of the time people are just writing them manually.
If I wanted input,
yep.
I would write them, and then and then the final real input that I give in all would be the plan. I will just move it.
Yeah, so typically the template is written when you decide what system you want to create. So you decide you want to create a sentiment analysis system. So you create a template that either says like, please specify the topic in the case of a model that was trained to follow instructions. Or if you have a base model that was not trained to follow instructions, which is rare nowadays, but GPT-2 or Llama 2 without chat tuning is an example of that. Then you would need to create a template that looks like this, where you put the model in a situation where the next word that follows up should be indicative of the answer to your question. So like positive or negative or something like that. So, but either way, like usually you handwrite this when you decide what task you want to do. Then this input X, this comes at test time. This comes when you actually deploy your system. So this would be like an Amazon review that you wanted to classify using a language model. Yeah. Cool. Any other questions? Okay, let's move on. So basically, this is what is happening behind the scenes. I don't know what OpenAI's format is because they won't tell us, of course. But I'm assuming that that's similar to what's happening in OpenAI too. Okay. So the next thing that we do is answer prediction. So given the prompt, we predict the answer. And so using whatever algorithm we want to use, we predict, fantastic here. And actually, it might not predict fantastic. It might predict something else. Like overall, it was a really fantastic movie that I liked a lot or something like that. So it might also do something like that. So based on that, we want to select the actual output out of the generated outputs. And I'm calling this post-processing. So for instance, we might take the output as is. So for something like just you interacting with ChatGPT or interacting with a chat model, you might be looking at the text as is. Or it might be formatting the output for easy visualization, selecting only parts of the output that you want to use, or mapping the output to other actions. So to give an example of formatting, this is a feature of ChatGPT or Bard or anything that you interact with. But I wrote, please write a table with the last 5 presidents and their birth dates. And ChatGPT is happy to do this for me. It says, here is a table with the last 5 US presidents and their birth dates. Joe Biden, Donald Trump, Barack Obama, George W. Bush, Bill Clinton. But this is written in Markdown, or I assume it's written in Markdown. So it basically makes this table and then renders it in an easy to view way. So this is really important if you're building a user-facing system because you want to be able to render these things. But the only thing a large language model can output is text, right? It can output a string of tokens. So this is a really good way to interact with it. I followed by saying output that in JSON format. So it says here's the information in JSON format. And instead of just giving me a big JSON string, it gives me syntax highlighting and all the other stuff like this. Presumably what it's doing here is it's outputting like a triple hash or something like this. The reason why I know that is because like seems to be making a mistake down here for some reason. Like outputting a weirdly formatted thing at the end. So even ChatGPT makes mistakes some of the time. So, cool. Another thing that you might want to do is, especially if you're not using it in like a directly user-facing application, but you want to use it to extract some information or make some classification decision or something like that. You often select information that's indicative of the answer. And so I love this movie overall. It was a movie that was simply fantastic. You can do things like extract keywords like fantastic and use that to indicate positive sentiment. There's various methods for doing this, and these are also used in the benchmarks that are used to evaluate language models. So it's, like even if you're not building an application directly, but you're just trying to do well in this class and get like a high score on a leaderboard or something, it's still useful to know about these things. So for things like classification, you can identify keywords like fantastic that might be indicative of the class. Another thing that's pretty common is for regression or numerical problems, you identify numbers and pull out the numbers and use those numbers as the answer. For code, you can pull out code snippets and triple backticks and then execute the code, for example. So all of these things are basically heuristic methods, but they can be used to pull out the actual answer that you want from the text that's generated by ML. Cool. Any questions about that? The final thing is output mapping. Given an answer, map it into a class label or a continuous value. And so this is doing something like taking fantastic and mapping it into the class positive. And so, if we want to extract 1 to 5 star ratings from reviews, this is something you would need to do. And very often it's like a 1 to 1 class to many word mapping. And by doing this, you can basically get a more robust mapping onto the number that you actually want. I actually coincidentally on Twitter saw a really good example of this like a week ago. Yeah, I don't know if I'm going to be able to find it in a reasonable time frame, but basically, there was a person who was using GPT-4 to create a model to like reward open source models for good and bad, responses. And they started out with giving it a 1 to 5 star rating, and then they switched it into very good, good, okay, bad, very bad, and then asked it to generate, those like very good, good, bad, okay, bad, very bad instead of 1 to 5, and that worked a lot better. Like the GPT model was a lot more like likely to get the answer correct than it was if you gave a 1 to 5 star rating. So this is something you should think about pretty seriously. And the way you can think about it is how likely was this data to appear in a large corpus of data on the internet? And it might be like a lot less likely that it's like, how good is this movie? 5, then how good is this movie? Really good. Like just think of like the occurrence probability. And you can even like mine this data from the web if you want to try to find out the best, like the best things there. Cool. Any questions about this? Yeah.
At the end of the day, the computer is just a finding variable ready. So how is it knowing or learning better?
So the model is predicting text. And like accurately, it's not even predicting the word fantastic. It's predicting the token ID like 73521 or something like that. But if it has seen that token ID more frequently after reviews than it has seen the token ID for the number 1 or the number 5, then it's more likely to predict that accurately, right? It's more likely to predict fantastic than it is to predict 5 star or something like that, just because fantastic is more frequent. And so because of that, if you think about like, what has it seen in all of the data on the internet and like model your answers here appropriately, then that can give you better results. This is a very important rule of thumb. Like, don't try to make a language model do something it's never seen in the pre-training data, and it will make your life a lot easier. So you can think about that going forward too. Cool. So next I want to move into few-shot prompting or in-context learning. So few-shot prompting, basically what we do is we provide a few examples of the task together with the instruction. And the way this works is you write an instruction like, please classify movie reviews as positive or negative, and add like input, I really don't like this movie, output negative, input, this movie is great, output positive. And this is pretty effective. The thing it's most effective for are twofold. It's most effective for making sure that you get the formatting right, because if you have a few examples, the model will tend to follow those examples with respect to formatting, especially if we're talking about like GPT-4 models or strong GPT models. It's also effective if you're using weaker models. So like stronger models like GPT-4 tend to be pretty good at following instructions. So if you say, please classify movie reviews as positive or negative, it will be more likely to just output positive or negative. But if you have weaker models, it might say input, I really don't like this movie, output, I think this is probably negative or something like that. It will, it might not follow the instructions as well, and it's more effective to provide as in-context examples. So this is a one thing to remember. One thing I should mention also is when I say few-shot prompting and in-context learning, these are basically the same thing. They basically refer to the same concept, but just from slightly different examples. Slightly different angles. Few shot is in contrast to zero shot. So zero shot means you're providing no examples. So zero shot prompting, you would have none. Few shot, you have several examples. In context learning means that you're learning how to do a task, but instead of providing the model with fine tuning data, you're providing the examples in the language models context. So they both basically mean the same thing, but they're just contrasting to like either a zero shot or fine tuning, which is why the terminology is different.
Well, yeah, so if they're not in a user-facing interface, and can you do few-shot prompting for the rendering?
Yes, you can definitely do few-shot prompting. I'm actually going to talk about exactly how you do this in like an OpenAI model here, which is for OpenAI models, there's a couple ways that you could do this. One way you could do this is you could have the role be user and the role be assistant, and just add like additional conversational history into the messages that you're sending to the language model. But actually the recommended way of doing this, which is in the OpenAI cookbook, which is in the reference, is that you send this as a system message, but you provide this like additional name variable here with example user and example assistant. The main reason why you do this is just because if you don't, if you send it in as the like user and assistant, the model might refer back to the few-shot examples as something that happened previously in the conversation. Whereas if you send it in the system message, it's guaranteed to not do that. So I think it's like less of an accuracy thing. It's more of a like, it's more of a prompt privacy thing than anything else. So this is their recommended way of doing this. On the other hand, if you're using like an open source model, you need to be careful because this name might not even be included in the prompt template. Like, for example, in the light LLM prompt templates that I was sending in, this is not even included at all. So you might just get a weird system message that is poorly formatted. So you need to be a little bit conscious of that. Cool. Any questions here? Does that answer the question? Okay. So one thing to be aware of is LLMs are sensitive to small changes in the in-context examples that you provide to them. So previous work has examined this from a number of angles. There's a paper by Liu et al., and they examine the sensitivity to example ordering. So like if you take the same examples and you just order them in different orders, you can actually get very wildly different results. And this is especially true for smaller models. So the smaller models here are like the GPT-2 models. The larger models here are like the larger model here is a GPT 3.5, I believe. Other things that people have looked at are label balance. So how important is it for the labels to be balanced? And if you're doing sentiment classification, for example, you might have only positive examples or only negative examples. And if you have only positive or negative examples, this can help or hurt your accuracy. For example, on this Amazon review data set, most of the reviews are positive. So you actually do better by having lots of positive examples in your in-context examples. On the other hand, for SST2, this is label balanced. So having only positive or negative is worse on average than having 3 positive and 1 negative. Another thing is label coverage. So if we're talking about multi-class classification, having good coverage of all of the classes that you want to include in your multi-class classification is important to some extent. But if you have more, you can also confuse the model, especially if they're minority labels. So if you have a whole bunch of like random minority labels, then that can cause problems. So this is something important to think about if you're planning on solving kind of like classification tasks. I've also had my own experience with using GPT for evaluation for machine translation. And when we use GPT for evaluation for machine translation, it was very important to add like high scoring values, high scoring outputs, low scoring outputs, some in the middle. And so it's also the case for regression problems as well. Cool. Any questions here? However, this is not super predictable. So there's not like any rule of thumb that tells you like this is, or as far as I know, there's not any rule of thumb that tells you this is the way you should construct in context examples. There are lots of papers that say they have methods that work better, but I don't know if there's any like gold standard industry practice for doing something like this at the moment. So just to give an example, this paper, it's a really nice paper examining why in-context learning works. One interesting finding that they have is they take in-context examples, but they randomize the labels. They make the labels wrong some of the time. So even with completely wrong labels, even with labels that are correct 0% of the time, you still get much, much better accuracy than if you use no in-context examples. And why is this? Probably, it's getting the model formatting correct. It's getting like the names of the labels correct, even if it's not accurate. So it seems like it's not really using these for training data. It's using them more just to know the formatting appropriately. Yeah.
This is just like when you give the in context of something, so we already have an idea of X when you're on this model.
Right.
Like, how is it mathematically? Like, is it just y1, y2? And I guess I'm just not seeing how you would incorporate that into the.
So you're not training the model at the moment. We're going to talk about that next class. But right now you're taking a model that has already been trained and you're providing it with a few examples, and then you're asking it to fill in the following examples.
It's just see the examples as an input.
Yes, exactly. And it's pretty amazing that that works in the first place, especially with a model that hasn't been explicitly trained that way. But there's a fair amount of research that I think we're probably going to be talking about in the interpretability class about why this happens. But basically, my interpretation for why this happens is because there's so much repetitive stuff on the internet, right? There's a bunch of examples of math problems, which is like question 1, and then the math problem, and then the answer. Question 2, math problem, and then the answer. So in order to model the text on the internet, it needs to learn how to be able to do these things, right? So, cool. The second thing is more demonstrations can sometimes hurt accuracy. So this is like binary classification versus multiple choice question answering. And actually with binary classification, the model ends up getting worse with more examples, probably just because the longer context, confuses the model or moves the instructions that are provided to the model farther away in the context, so it starts forgetting them. So basically, what I want to say is, this is more of an art than a science. You might not get entirely predictable results, but don't worry, it's not just you. Cool, yeah. It can't. So the question is, if the in-context examples reflect the data distribution well, would that boost the accuracy? I think the answer is probably yes. Yeah. I don't know if it's that clear, because like what I would expect is better coverage is probably more important than better representativeness. So like, even if you have some minority labels, it's probably better for the model to know what those minority labels look like. And that's going to be especially true for like stronger models, I think. So, yeah. Cool. Okay. So next I want to talk about chain of thought prompting. So chain of thought prompting is a very popular way of prompting models. And the way it works is you get the model to explain its reasoning before making an answer. And so, sorry, this example is a little bit small, but like the standard prompting method is like Roger has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many tennis balls does he have now? The answer is 11. And so this is an in-context example, and then you have your input, which has a different problem. The cafeteria has 23 apples. If they use 20 to make lunch and bought 6 more, how many apples do they have? The answer is 27. And so this is wrong. So what chain of thought prompting does is, instead of just giving the answer, it gives you an additional reasoning chain that says Roger started with 5 balls, 2 cans of 3 tennis balls. Each is 6 tennis balls, 5 plus 6 equals 11. The answer is 11. And so then when you feed this in, basically the model will generate a similar reasoning chain, and then it's more likely to get the answer correct. And this very robustly works for many different problems where a reasoning chain is necessary. And if you think about the reason why this works, I think there's basically 2 reasons why. The first reason is, I only wrote one on the thing here, but the first reason is it allows the model to decompose harder problems into simpler problems, and simpler problems are easier, right? So instead of immediately trying to solve the whole problem in a single go, it will first solve the problem of like how many are left after you use 20. And so it gets 3. And so now it has this 3 here. So now it can solve the next problem of adding 6. That's equal to 9. So it's solving simpler subproblems than it is compared to harder ones. Another reason why is it allows for adaptive computation time. So if you think about like a transformer model, if you think about a transformer model has fixed computation time for predicting each token, right? You have a fixed number of layers. And based on that fixed number of layers, it passes all the information through and makes a prediction. And some problems are harder than others, right? So it would be very wasteful to have a really big transformer that could solve, really complex math problems in the same amount of time it takes to predict that the next word is like dog after the word the big or something like that, right? So there are some things that are easy, we can do in a second. There are some things that take us more time. And essentially, this chain of thought reasoning is doing that. It's giving it more time to solve the harder problems. Yes. Okay. Yeah, good question. So that's what this next paper does. So the question was what happens if we just ask it to reason? And the answer is it still works. And this paper was really like I love this paper for its simplicity and cleverness. And basically they contrast few shot learning, few shot chain of thought, where you provide chain of thought examples, 0 shot prompting basically, and 0 shot chain of thought. So what they do is they just add let's think step by step, that they add that phrase to the end of the prompt. And then that elicits the model to basically do chain of thought reasoning without any further examples of how that chain of thought reasoning works. Why does this work? Again, because like on the internet, there's a bunch of examples of math problem solving data sets or QA corpora where it says, let's think step by step. And after that, you consistently have this sort of reasoning chain added there. So good intuition that this paper answers the question, and this like actually does work. One interesting thing is now, if I go to ChatGPT and I say, I am teaching a class with 98 students, 70% turn in the assignment on time, 10% turned it in late. How many did not turn it in? Let's see if this works. Okay, it's writing code for me. That's a feature slide. I kind of didn't want it to do that. Okay. Do not write code. Okay, so it's a little bit slow. Okay, so there that worked, but note that I did not say let's think step by step. I didn't ask it to do this. And the reason why is we're going to talk about instruction tuning next time, but basically GPT has been tuned to do this reasoning even if you don't ask it to do that. It wouldn't do that naturally, but it's because lots of supervised data has been added into this model. So like another thing is like if you are planning on doing anything about like chain of thought reasoning or stuff like that as a class project, you need to keep in mind that the like GPT models have already been trained to do this. And so if you want to like try to find out a better way to elicit this from a raw model, you'll need to use a raw model like Llama 2 with no chat tuning or stuff like that in order to do that in a neutral setting that hasn't been contaminated by like supervised training data. Cool. Any questions? Okay. So next I want to talk about prompting in programs. That ChatGPT gave me a good example of why this is useful or important. So there's two results. Actually, both of these are from my collaborators. But the first one is it demonstrates that structuring outputs at programs can help you get better results, even if the task isn't a programmatic task. So this is kind of interesting. So we were looking at predicting structured outputs, and these structured outputs specifically are procedural knowledge like this. So like, how do we cook a pie? Or how do we serve pot pies on a plate? And we had this procedural knowledge, like take the pies out to cool, open the cabinet drawer, take out several plates. And we wanted to know the dependencies between these so we could create a structured like procedural knowledge base. So this is not an inherently code-based task. It's not a, you could just ask the model in natural language and that would work as well. So we structured things in a couple varieties. So we had a textual format. We had something in the dot format, which is a way to draw graphs. And then we also tried structuring the output in Python. So these are just different ways to format the output. They all say the same thing, and we can extract the answer from all of them. But we found that structuring it in Python basically is the more effective way of doing this. So why is this the case? The answer is essentially the same thing that I was talking about before with, predicting excellent instead of 5, right? It's seen a ton of Python in its training data. So it's very good at predicting Python. It's less good at predicting dot format because it's seen less dot format and it hasn't seen very much text here. Another comment is code is very highly structured compared to natural language. And because code is very highly structured, we have things like dependencies where we refer back to variables that we defined before and other things like this. So I think when it starts outputting code, the models get into this mode which say, yes, please refer back to the things you've seen previously more often. Like attend to previous stuff more often and don't just like generate things, arbitrarily and hallucinate, new content. And because of this, for generating structured outputs, even if the structured outputs don't need to be code, you can benefit by doing this. Another thing that's a really handy trick is anytime you want to get a structured output out of a model, you can ask it to generate something in JSON instead of generating it in text. And the reason why JSON is useful is you can parse the JSON, you can pull out the strings and other stuff like that. So this can be very effective because if you just add an instruction that says, please format things in this particular format, often the model won't listen to you and it will output something in a different format. You need to write a really annoying parser to pull out the information that you actually want. but it gets JSON right almost all of the time just because it's seen so much JSON. So that's a nice trick if you want to do something like that. Another thing is a paper called Program-Aided Language Models that we did about a year ago. And the method that we proposed here is using a program to generate outputs, and this can be more precise than asking an LM to do so. And so instead of doing chain of thought prompting, we created a few shot examples where we wrote like the text here, and then the text in English, and then we had code, corresponding code, the text in English, corresponding code, and then the answer is, and then the final code. And then we basically generate this code and execute it to get the answer. So like, as you saw, this is implemented in ChatGPT now. It's you write something out, it will decide whether it wants to generate code or generate text, depending on the type of problem. And it's just more precise. It can solve like actually rather complex problems, like calculating how much tax you need to be paying or something like that. It's especially useful for numeric questions, and it's implemented in things like the ChatGPT code interpreter, Bard code execution, other things like that. It's pretty cool. It can actually do visualizations for you for papers also. So if you ask it to visualize data for you, ChatGPT now does a pretty good job of doing this. Like, to give an example, I gave it a big Python list and asked it to generate a histogram, and it did a really good job of it for me. It also gives you the code so you can go in and modify it later. So I would definitely recommend, thinking about using this either in your research or just to write your reports for this class. So, this class is generative AI friendly mostly. So like, I do want you to learn the things we expect you to learn, which is why I suggest that you don't like just write everything for assignment number 1 with ChatGPT. But I think even if you tried to do that, it'd probably get it wrong in subtle ways. So you're probably better off understanding the content anyway. So, cool. This can also be expanded a whole lot into like agents and tools, and I'm going to talk about that separately later. Cool. Any things about this? Okay, I'm going to go next. So prompt engineering. When you're designing prompts, there's a number of different ways you can do this. You can do this manually. To do this, you configure a manual template based on the characteristics of the task using all of the knowledge that I told you before. You can also do automated search, and there's a number of different ways to do automated search for prompts. The first one is doing some sort of search in discrete space. So you find a prompt that is essentially text. The other one is search in continuous space. So you find a prompt that isn't actually comprehensible text, but nonetheless is a good prompt. So looking at manual engineering, making sure that the format matches that of a trained model, such as the chat format, is actually really, really important. And this can have a large effect on models. There's a really nice paper that demonstrated this convincingly before, and also releases some software that allows you to do this kind of in an efficient manner. And what this is showing is this is the original formatting of a prompt that was given, I believe, by some sort of like machine reading or document-based question answering data set, which was like passage answer. If you modify the spacing between the fields, that increases your score by several percentage points. If you remove the colons, that increases your score by a few more percentage points. It's kind of silly, but like little things like this actually can make a really big difference. If you modify the casing, this decreases by a lot. If you modify the casing and remove colons, so the thing that was useful, like adding colons here, remove colons, that further decreases. If you forget to add a space between the passage and the text, that really hurts your accuracy. So this is pretty painful, right? Like you don't want to be getting 0.036% accuracy when adding a space would give you like 75% accuracy, right? And one interesting thing is, this is looking at different models. And with different models, it's pretty consistent that many different plausible formats that you try, the average gives you a really low accuracy, but there's a few outliers that give you really good accuracy. And these probably correspond to the things that it was trained on, instruction tuned on, or other things like this. So number one, make sure you're using like the canonical prompt formatting for the model for sure. Number two, you might want to do a little bit of additional search to see if you can do even better than that. So this is something to be very aware of. Okay. Do you have a question? This is dependent on what it sees in training time. Another thing actually is this will definitely be tighter for like a ChatGPT or GPT-4 because it's been trained on many different formats at training time. And so the better the model has been trained on a lot of different formats, the less this is going to have an effect. But you're probably not going to be retraining a model that somebody gives you. So like this is something to be very aware of if you're just a downstream user of the model, especially in open source mode. Another thing is, how do you give instructions to models? Instructions should be clear, concise, and easy to understand. One very funny thing is, I think now, like actually prompting language models is very similar to prompting humans, especially if we're talking about like GPT-4. So if you're not very good at explaining things to humans, that might actually be bad. And you might want to practice that. And explaining things to models might be a good way to practice that, right? So, it actually could give you feedback without annoying your friends by having you explain things to them in several different ways and seeing how they react. So, but anyway, clear, concise, easy to understand is good. There's this prompting guide, which I can open. This has a prompt engineering guide. I like this site, but it does have a bit of like variance in the importance of the information it tells you, but like this particular page is nice, I feel. So start simple, start with simple instructions. You should tell the model what it should be doing. So make sure you say write, classify, summarize, translate, order, and things like this. It also gives some good examples of the level of specificity that you should be giving. So something that's less precise is explain the concept of prompt engineering, keep the explanation short, only a few sentences, and don't be too descriptive. Use 2 to 3 sentences to explain the concept of prompt engineering to a high school student. So what this does is this tells you the level of the reading level. So this doesn't even tell you the reading level, I guess. And then 2 to 3 sentences is more precise than keep it a few sentences, don't be too descriptive. So the more precise you can be, the better it is. One interesting thing is like, if you ask your friend to do something and they don't know how to do it, they'll complain to you. But right now, LMs don't complain to you. They may in the future. That might be like actually an interesting thing to find. The interesting methodological thing to look at for a project or something like that. But right now you need to be precise, and like it doesn't give you feedback when you're not being precise, so you need to be there. Separately from this, there are methods for automatic prompt engineering. So prompt paraphrasing, gradient-based discrete prompt search, prompt tuning, prefix tuning. So prompt paraphrasing, this is a method that we proposed a while ago to basically paraphrase an existing prompt to get other candidates. It's rather simple. Basically, you take a prompt, you put it through a paraphrasing model, and it will give you new prompts. And this is good because it will tend to give you things that are natural language. You can paraphrase 50 times, try all of them, see which one gives you the highest accuracy, and then use that one. There's also an interesting paper that demonstrates that you can do this iteratively. So you paraphrase once, you filter down all the candidates that do well, and then you go in and paraphrase them again, and you just do this over and over again. And that can give you better results than kind of one-off paraphrasing. So that's very simple. You can even use a large language model to do the paraphrasing for you. Another thing that you can do is gradient-based search. So the way this works is you need to have a model that you can calculate gradients for. And what you do is you create a seed prompt, and then you calculate gradients into that seed prompt. So you treat each of the tokens here, like T1, T2, T3, T4, T5, as their own embeddings. You do backprop into those embeddings and you optimize them to get high accuracy on your data set. Then after you're done optimizing them to get high accuracy on your data set, you clamp them onto the nearest neighbor embedding that you already have. So you basically say, okay, the nearest neighbor to the embedding that I learned is atmosphere, then a lot, dialogue, clone, totally. And so this will actually give you better results than paraphrasing in many cases because the search space is less constrained. You can get these very unnatural prompts that don't seem to make sense, but actually work well. This has particularly been widely used in adversarial attacks on language models. So how can you come up with prompts that cause language models to do things that you don't want them to be doing? And there's actually this nice paper also by people at CMU called Universal and Transferable Adversarial Attacks on Line Language Models. And basically what they do is they try to optimize the prompt to create a prompt that causes the model to do bad things, basically. And they try to do it even on models that have been trained to not do bad things. And they demonstrate that, number one, you can cause things like models like Llama to do bad things, like output toxic things, tell you how to build bombs, stuff like that. But also the same prompts also work on like GPT models, which is kind of like interesting and very, confusing in a way because you thought this might be exploiting idiosyncrasies of a particular language model, but actually it's not. So I find this kind of fascinating. So if you take that a step further, one thing that you can do is you can say, oh, actually, there's no reason why we need to clamp these embeddings back to an existing embedding, right? So we could just optimize the prompts, the embeddings of the prompts that go for a task, and not clamp them back to embeddings and just keep them as is. So what I mean by that is like right here, it's optimizing T1, T2, T3, T4, T5, and then clamping that back to atmosphere, a lot, dialogue, clone, totally. But just keep them as is and don't worry about them like actually being a token in the model. Because if you have control over your model, you can just add them as new elements in the vocabulary and you're fine, right? So what they demonstrate in this paper is that instead of taking your 11 billion parameter model and training the whole 11 billion parameter model for many different tasks on many different data sets, they just train these prompts, which are like 20K parameters each. I forget how long it is. It's like 10 tokens or 20 tokens or something like that. And train it on all of the data sets here. And you don't actually need to do multitask learning. You don't need to train on multiple tasks at the same time. You can just train on a single task. So now let's take that even a step further. So this is only training the embeddings that you input into the model. There's a method called prefix tuning. And the way prefix tuning works is instead of training only the embeddings that go into the model, they actually train a prefix that you then append to every layer of the model. So prompt tuning basically does this for the first layer of the model. Prefix tuning does this for every layer of the model, and you append a prefix for every layer. So it's just a more expressive version of prompt tuning, essentially. So these are all kinds of gradual steps from a human created prompt into something that is basically training a prompt or a prefix to the model. So I would take questions, but let me get to the end of this section also because I think there's interesting analogies here. So in the next class, I'm going to talk about parameter efficient fine-tuning methods, which is kind of a more general, it's a more general version of prompt tuning or prefix tuning. There are methods that tune a small number of parameters to get the model to do something. And there's a bunch of different parameter efficient tuning methods. Many people may have heard of something like LoRa or adapters. I just talked about prefix tuning. So essentially, prompt tuning and prefix tuning are part of this more general class of parameter efficient fine-tuning methods. And so what we can say is actually prompting is fine-tuning. Prompting is a way of fine-tuning the model or getting the model to perform a particular task. And we have this taxonomy of, we have prompts in natural language that are created by humans. Actually, maybe I should say manual prompt engineering here. This was first done in the GPT-2 paper, where they demonstrate that models could solve tasks by doing it this way. Prompt paraphrasing is a step up from this because it's no longer relying on human engineering, and you can, expand to a broader set of prompts. It can always start with human created prompts, so it's kind of like broader than that. Discrete prompt search doesn't necessarily need to rely on a paraphrasing model. It could rely on like gradient-based models or something else like that to give you something that's not actually natural language, kind of just random tokens. Continuous prompts or prompt tuning is a step above that. Multi-layer continuous prompts or prefix tuning is a layer above that. Parameter efficient tuning is more general than that. And then you have all training methods, so including fine-tuning your model. And so what are the implications of this? I think, so a lot of people when prompting came out, they were like, prompting methods are very hacky. I don't like how we have to do manual prompt engineering. It seems like a dark art as opposed to like, actually, some sort of well understood fine-tuning method that we could use. But I actually like them. I like prompting a lot because if anybody is familiar with like Bayesian statistics or machine learning, we have the concept of like a prior probability over parameters, and then a probability that we get after fine-tuning the model or after training the model. And prompts, in a way, are our first like good prior over neural network models. They give us the ability to specify what task the model should be doing, or like a general idea of what task the model should be doing before we ask the model to actually do the task. And so we can either use that prior as is, we can use the prompted model as is without doing any additional tuning, or we could take the prior that we have given to the model by using a natural language description of the task it should be doing, and then combine it with fine-tuning. So we can take the prompted model, we can initialize the distribution of this like task A prompt using a human created prompt, and then go on and fine-tune it on lots of training data as well. And there's a method for doing that by Schick and Schutze called pattern exploiting training, where they do exactly that. They basically initialize with a manually created prompt, and then they fine-tune the model on fine-tuning later after that. So that's the reason why I like prompting-based methods. They give us this like really nice way to very quickly create a system, but we can also have whatever level of additional training on top of that. Cool. So that's a little bit early. I'm